We're back. We're back to doing logic, of course, but we're also back to the canonical form of logical proof, deduction, what some people still call natural deduction. Anyway, whatever you call it, the form of logical proof that uses rules of inference and replacement rules to advance from premises to conclusion. I wouldn't say it was a detour to truth trees. I did want to make sure that truth trees had their moment in the sun. The time that we had already spent on rules of inference and replacement rules were enough to show roughly how deductions work, just as the time that we spent on truth tables sufficed to show how they work. And I wanted to give equal time to truth trees because we've really been using three kinds of test or demonstration of validity in our work on propositional logic. In that sense, what we're doing in the present session is not new ground. It's not a new way to demonstrate validity. It's an additional set of tools that we can use with the deductive method in order to make that method more powerful and more flexible. Of the topics in the present chapter of Clenk, I'll be covering conditional proof, indirect proof, and theorems. And of the three, if only one really stays in your mind as a result of today's session, I do hope that it's conditional proof. This is not to say anything against proving theorems, but the way we're proving theorems in this chapter is very much based on the methods of conditional proof and indirect proof. They're just one application of those methods. As for indirect proof itself, as one way of doing proof within proof, it's terrific. It's, as the textbook indicates, an age-old method. But at the same time, it's not particularly innovative. It's an indirect proof. You posit the negation of the conclusion and you see what happens. In that sense, the principle motivating indirect proof within the proof is really just the principle that motivates truth trees. And I already indicated how impressed I am with truth trees, which, in my opinion, manage the process of indirect proof much more elegantly than deduction. Okay, well, this is all my way of saying I hope you're ready for conditional proof, because it's really something pretty special. Conditional proof is up there in my book with large-scale multiplication of multivariable, of multi-digit numbers, and with long division as processes that some very insightful people figured out that could be mastered and used in a comfortable way by just regular people. Okay, that's the really brilliant thing. Think about that with long division. You learned it in third grade. It wasn't a third grader who made it up, though, I promise. What is the story with conditional proof? Conditional proof builds on the relationship that we've seen and commented on several times between the material condition and the logical relation of implication. Remember that a valid inference, a valid implication, and the material conditional both have this feature that the one thing you're not allowed to have is the first part being true and the second part being false. In a conditional, you cannot have a true antecedent and a false consequence. And in a valid argument, you cannot have true premises and a false conclusion. So how are these two related in conditional proof? Well, when a proposition P implies a proposition Q, the conditional statement P horseshoe Q, if P then Q, is true, is logically true. The converse is also true. when the conditional statement, if P then Q, is true, then P implies Q. And then similarly, we can define the equivalence between two statements as the truth, the validity of the biconditional between the statements. So if I ever start, here's why this matters. In any proof, if I start with P and I wind up with Q later in the proof, I have shown as a logical statement, as a logical truth, that if P, then Q. Right? I am proving the truth of if P then Q. No other connective works this way, okay? Because only the conditional is intimately related to logical implication. Now, the second insight behind the conditional proof is that you can run a proof inside another proof as long as you never lose sight of the borders of the inside proof. Okay, the inside proof runs on the basis of assumptions that have been inserted just for this purpose, just for the purpose of this inside proof. And when we want to return to the main stream of thought, we abandon those assumptions, what's called discharging the assumptions. If you want to have more than one conditional proof inside a proof, well, one can come to an end and then you begin another one. Or you can have one nested inside the other. But they never overlap, right? And this is one thing to keep in mind from those little lines you draw on the left side of the proof. The lines should never cross. We can start with a very simple example where we pretend to use as a premise the antecedent. We arrive at the consequent, and therefore we deduce the validity of the logical truth, rather, of the conditional. Now, pretend you don't know that famous rule that you just spent the last few weeks getting familiar with called hypothetical syllogism. We've made great technological progress. Remember, everything used to be on white chalk on blackboard. Take a look, black ink on white paper. So suppose we have a premise, if A then B, a premise if B then C, and a premise if C then D. And we want to arrive at the conclusion if A then D. Well, it's you see, because you know the hypothetical syllogism, you know that this is just a reiterated application of the hypothetical syllogism. As I say, pretend you don't know that so that we can demonstrate conditional proof in a simple example. Okay. We're trying to prove the truth of this conditional, A horseshoe D. So we put in an assumption, which is a pretend premise, okay? And we call this an assumption. CP, an assumption made for a conditional proof. Okay, now, all right, well, we don't have the hypothetical syllogism, but we're not exactly on a desert island here. We've still got full and ample use of modus ponens. Let's have a look. Well, you immediately see that from premise 1 and from line 4 taken together, you can use modus ponens and come up with B, right? If A, then B, A, therefore B. You now look up to line 2, and you see how you can reapply modus ponens. The pattern is clear. Now look up at line 3. If C, then D, and you've got C. We've now arrived at the conclusion D. Well, we haven't proved D. You got to be careful here. This is not a proof that D. It looks like a proof that D. It's only a proof that D, given this additional assumption, which is not in the premises, this additional assumption of A. By conditional proof, lines 4 through 7 give you line 8, right? You started with A, you wound up with D, and then line 8, and I actually like the way the textbook puts this. Line 8 does not appear in that conditional proof, but it is a description of, a summation of that proof, okay? It's saying, well, when we did this and got this, we therefore demonstrated if A, then D. Now, I did mention the only other connective that's really related to the conditional here is the biconditional. Let's do another example where we're trying to prove a biconditional, as you might expect. Proving a biconditional amounts to running two conditional proofs, one after the other, and proving two conditional statements. All right, here we've got the premise. If A or B, then A and B. And we're seeking to prove A if and only if B. All right. Well, as I said, it's a biconditional, A if and only if B. You might expect, and in this case you'd be right, that you want to break this down into the two conditionals, if A, then B, and if B, then A. All right, so first we're just going to try to prove if A, then B. And what will we do with a conditional proof? We will posit the assumption A for the purpose of the conditional proof. That's an assumption. All right then. We posited A because we want to get to B. We want to take A and use it in that long conditional statement that is the first premise. I think it's easy to see how we're going to do that. By the rule of inference called addition, we go from A to A or B. We can now use this new line, A or B, up there in premise 1 and modus ponens. But once we have A and B, it's the work of a moment to see that from A and B, we can infer B alone. That's simplification from 4, all right? So now we've completed the first conditional proof that we need in this larger proof. Okay. I'll go quickly through the next half of the proof because it's absolutely the same as the first half. We're going to create a new conditional proof starting with B, ending up with A. We go back to the same first premise, use this, actually the same antecedent. We simplify line 9 to be A alone. And we have if B, then A. Still 2 little steps. That's conjunction from lines 6 and 11. And by biconditional exchange, which is to say the replacement rule that analyzes the biconditional into a conjunction of conditional statements, we get a if and only if B, which is just what we had wanted to prove. All right. And now we're still at it. So this is the basic idea of the conditional proof. It's really so simple that you might not notice while you're doing it what a remarkable technique it is. And as Clenk remarks in the book, it's a technique that permits us to run a lot of proofs that otherwise would be just horrendously long. Now, the indirect proof ought to strike you as very much the same thing as the conditional proof. As in the conditional proof, we build a proof within the proof. As in the conditional proof, we do so by making, you might say, pretend premises. We posit assumptions just for the duration of this proof within the proof. As in the conditional proof, when we arrive at a provisional conclusion within the proof, that's not actually our conclusion. We summarize the result of that internal proof. The difference is that in the indirect proof, it's really much simpler. We hypothesize the negation of a conclusion that we're interested in. It could be the conclusion of the whole argument, doesn't have to be. The point is we're trying to get somewhere, and we hypothesize that the conclusion we're trying to arrive at is false. Then we have to deduce a contradiction. Having arrived at a contradiction, we can therefore conclude that our hypothesis was wrong, okay, got us involved in an error and a contradiction. And if the hypothesis was wrong, then the statement negated must be true, there being only two truth values in our system, true and false, and therefore the original conclusion we wanted to prove is indeed the case. Now, a proof can very easily use both a conditional proof and an indirect proof. Often it has to. You're doing a conditional proof, and then you think, okay, how am I going to get at this desired consequence to the conditional? Well, let me hypothesize the falsity of that consequence, come up with a contradiction, and therefore I'll have completed the conditional proof, right, within the larger proof. Now let's have a look at this example of an indirect proof. It now gets a little bit longer. If P, then S. If S, then not B and D. If not B, then T. Not, parentheses, if D, then T. Okay. We assume, we hypothesize the falsity of the desired conclusion. The desired conclusion is not P, so we're going to hypothesize P. Well, it's easy to see what to do next because P only appears in one of the premises. That's the first one. So by modus ponens, P gets us S. And then you can see S only appears in the second premise, and again by modus ponens, from lines 2 and 6 gets us the negation of B and D. Well, by now you're old hands with at least one of the rules of replacement, that is De Morgan's law. By De Morgan's law, line 7 becomes not B or not D. Okay. What do we do next? Well, there are different ways to proceed now, but this is a good example of making sure that you've done everything you can with all the premises. And in this case, we've looked at and used premise 1 and 2. We notice there's a slightly more complex premise in line 4, the negation of if D, then T. By conditional exchange, we know that if D then T is equivalent to not D or T. So we've got the negation of that. And by De Morgan's law again, we have D and not T. Okay. Now this might not seem like enough yet, but you see that you've got the D, and you see that you've got a disjunction just a few lines up that has the negation of D. So you're going to be able to use the disjunctive syllogism. For now, we simplify the D and not T to get rid of that not T. We want only the D. We might want to come back. You can always come back when you're doing a simplification of a conjunction. So by the disjunctive syllogism, going to lines 8 and 11, we wind up with the negation of B. And now we can return to that other premise, line 3, if not B, then T. Using modus ponens, we go back up there and we get T. And now, remember I said we could come back to that D and not T. We're going to come back to it. We're going to simplify it again, but this time to the not T. And we conjoin the T and the not T, we have a contradiction. In that inside proof, in that indirect proof within the larger proof, we started by assuming P, and we arrived at a contradiction. Notice the contradiction does not have to be a contradiction of P. That's what's misleading about sometimes saying, calling this a reductio ad absurdum. It can lead people to think that you posit a certain statement and then you arrive at the contradiction of that very statement. Well, that can happen. Maybe that's even the gold standard of indirect argument, maybe. But what's true, what's clear, is that if any contradiction arises anywhere, okay, if you've got any contradiction anywhere as a result of having posited this negation of the conclusion, okay, that tells you the conclusion is true. Okay. We tried the alternative, we tried the negation. That didn't work. And therefore, we can infer the conclusion, the negation of P. Okay. Maybe this could be done in a quicker way. I have a hunch if you came knocking on this on the door of this proof with the truth tree, why that truth tree would do the job pretty well too. But after all, the truth tree is just another form, a schematic form, an immobile form, as it were, of the indirect proof. Okay. Now, as the textbook makes clear, and this is important to repeat, a single proof can contain both a conditional proof and an indirect proof. That's what happens when the sketch pad is used, both to teach logic and to teach drawing. Okay, now we're going to do one a little bit quickly that combines a conditional and indirect proof. It's a simple, well, simple enough proof. It has only two premises, but a slightly thorny conclusion. This desired conclusion says, if A or D, then not C and F. Now, we're going to set up a conditional proof, and then immediately we're going to run an indirect proof. We're going to set up a conditional proof using the antecedent of this conditional that we're trying to prove the truth of in the conclusion. We're going to take that antecedent, make that the assumption that motors, that initiates the conditional proof, and then immediately we will negate the consequent in order to derive that and to demonstrate the truth of the conditional statement. Okay, there's our assumption for the conditional proof. And we want to show the consequent of that conditional. So when we're aiming at the negation of C and F, what are we going to posit? Sorry, yes, we're going to posit C and F. That's the assumption at work in the indirect proof. Well, how are we going to do this? You notice that line 1, the first premise, has a negated C in the consequent of that conditional. That kind of tells you what we can do with this assumption of the indirect proof. We're going to simplify it to a C and then use modus tollens. Right? Modus, this has a not C in the consequent. So a C comes along, is the negation of that. And so we get the negation of A or B. By De Morgan's law, we get not A and not B. Are you seeing it? Yeah. We're now going to go back not to one of the original premises of the argument, but to the assumption of the conditional proof. Okay. The indirect proof is nested inside the conditional proof. And so you might say, even though in real life, that assumption that starts off the conditional proof isn't really true, it's not really a premise, it's pretend. But within the world of the conditional proof, which is where the indirect proof is doing all its living, that pretend premise, functions as a real premise, okay? So A or D, which we posited in order to get the whole conditional proof started, can now function as a premise in the indirect proof that's nested inside the conditional proof. We simplify 7 and get the negation of A. We take that back up to line 3. I know someone who spoke French and liked this abbreviation of disjunctive syllogism because, you know, when you pronounce those letters as initials in French, déesse, right? That's the French word for goddess, déesse. So that you see, that's the goddess rule of inference. Maybe I said that already when we were doing rules of inference. In this case, DS gives us a D. And now you see how we can go back up to the second premise and derive, again, by our old friend, the standby, the bread and butter rule, modus ponens, we can get the consequence of that. Maybe you see where we're heading with this. From not F and not G, we can derive not F by itself, simplifying. And remember, way up here, we started with C and F, the assumption for the indirect proof, and we simplified it to C because that's what we wanted to use, but we can always simplify it again, go back and derive the F. The conjunction of 11 and 12 gives us F and not F. That's a contradiction. We can go no further. What got us into all this trouble? Well, you know what it was. It was hypothesizing the negation of that conclusion up here. So the indirect proof brings us to the negation of C and F. And that means that the conditional proof took us from A or D to the conclusion not parentheses C and F. Which is the conclusion that we wanted. Right? We ran a conditional proof with an indirect proof inside it. And look, maybe one of you out there looked at those two premises and said, oh, it's just trivial that you can deduce if A or D, then not parentheses C and F. it's a 57-step proof as long as you yada, 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 maybe. But the very powerful tools of conditional proof and the powerful but more familiar tool that we call indirect proof allowed us to accomplish this even when we were spelling out every step in painstaking detail in barely over a dozen steps, right? That's a good proof. That's a relatively speaking, quite quick proof. Now, we can do some harder examples, right? But I wanted to emphasize the fundamental rules, principles for using conditional proof and indirect proof. In a way, the topic of the theorems, is an addendum here. It's very important, don't get me wrong. A theorem in logic is slightly different from a theorem in geometry, in that in geometry, you always have to be aware of the more fundamental premises within geometry that make that theorem true. Ultimately, you go back to Euclid's postulates if you have to, and wind up with the theorem. A theorem in formal logic is different in that you should be able to prove the truth of the theorem without any premises. That's a little misleading. You are using something. What you're using are the rules of inference and the replacement rules. You're using them. You're treating those as more or less as axioms of the logical system. They're not quite axioms. That is, you don't really need that many axioms. You need a couple of really fundamental axioms like modus ponens, and you can crank out all the others. But the idea is you're helping yourself to all of those, just as in geometry, you help yourself to the 5 postulates. In any case, when you're proving a theorem in logic, because you don't have to announce those rules of logic that you're using, you conduct the proof without any premises. And this is why we combine the topic of theorem together with the topics of conditional proof and indirect proof. Because in a deduction, conditional proof and indirect proof are the only way to get a proof moving if you're not given any premises to start with. That's because of their function, is what I was calling pretend premises. So you're looking at a theorem, you've got to prove the truth of this theorem. A theorem is a tautology, after all. You want to prove the truth of this theorem, and you don't have any premises, okay? So you set up either a conditional proof or an indirect proof or some combination of the two, positing what you'll need in order to demonstrate the truth of the theorem. Okay, then. There's a theorem. Pardon me a moment while I write it. It's a big, long conditional. If A horseshoe, parentheses, B horseshoe, C and D, then if A horseshoe B, then A horseshoe D. Okay. Remember, there are no premises. Where do we begin? Well, I think it's natural in this case to see it's going to be a conditional proof. We're going to start with the antecedent and we're going to arrive at the consequent. But you notice that the consequent is itself a conditional. Well, it's a conditional with conditionals, but still, even if we don't get into that level of detail, we see that the consequent itself is a fairly complex conditional. And so what we're going to do is we're going to set up a conditional proof starting with this antecedent, and then we're going to run a conditional proof starting with this antecedent, if A then B, with a little indirect proof thrown in there. It won't even be 20 lines. Watch. Now, the assumption for the sake of the conditional proof is this antecedent. There are different ways you can go with this. One of the fun little replacement rules, doesn't get used that often, but you notice it because it's a little different from the humdrum other replacement rules, is exportation, right? And from line 1, exportation gives you if A and B, then C and D. That's a conditional, okay? And that means you can change it into a disjunction and then arrange the parts of the formula you wind up with. You'll see what I'm doing as I go here so I can keep this next part brief with a minimum of commentary. Okay, what did I do? I took this conditional, I used conditional exchange to turn it into a disjunction with a negated antecedent. I distributed the negation just in the one part of that line to turn the conjunction into a disjunction of negations. And then here's the only, I won't even say trick, I won't glorify it with that name. The only unexpected step, I just rearranged it. We have a disjunction here. We have not A or B or the C and D. So I just moved the not A together with the C and D and put the or not B on the outside. Can you do that? Of course you can. It's association. If two go with one, you know, that one can go with the other two. But now, we've, as it were, done what there is to do with that posited antecedent to the large conditional, to the conditional that is the entire theorem. Let's take a look at the consequent, okay? And we're going to prove the consequent, which is itself a conditional, this time by positing, by hypothesizing, by assuming the antecedent to that conditional. right? We're starting another conditional proof inside the conditional proof. We're doing a conditional proof showing that given the antecedents to the theorem, all right, then if you've got the antecedents to the consequent, you can have the consequent to the consequent, which is going to be A horseshoe D. All right. And we're going to do that by indirect proof. That is, we're starting a conditional proof and then immediately starting an indirect proof inside it where we negate this consequent if A then D. For the purposes of an indirect proof. Moving just a little faster here, I'm doing two steps at once. I turned that A horseshoe D into not A or D, then negated it using De Morgan's law, getting A and not D. Don't try this at home, kids. It's just to speed things along. Now, what we wanted from that, or what we want for now, is the simplification of A and not D to give us just A. And we're going to use A together with the assumption that powers this second conditional proof to give us B by modus ponens. And now I think, well, you probably saw already, but I think you now see indubitably what the next step is going to be. Here's a B. Remember, we rearranged this line. We rearranged the antecedent to the entire conditional proof, to the whole big conditional proof, so that it was a disjunction with an or not B. And now here we are with a B. That means we can use the disjunctive syllogism. On 5 and 10. And now you're looking at this and say, not A or C and D. That looks like a familiar form. Yeah, because the conditional exchange, remember, is a replacement rule that you can use in either direction. You can start with a conditional and make it a disjunction, but you can also start with a disjunction and turn it into a conditional. That would be great if we had an A. Wait a minute, we've got an A by itself in line 9. Okay. Remember, although there's a conditional proof going on here, we're immediately in the midst of an indirect proof. We want to arrive at a contradiction. Let's not forget the prize. What did we do there? Well, we had the C and D conjunction, simplified that to a D. Back up here, right at the beginning of the indirect proof, we had an A and not D conjunction, already simplified it to get an A, simplified it again to get a not D, conjoined the D and not D. The result of this positing, not parentheses A horseshoe D, the result of this hypothesis, this attempt to negate that conclusion, was a contradiction. We didn't actually prove that D and not D, you understand. What we proved because of all this was A horseshoe D, right? Because we got into so much trouble when we tried to live without it, okay? And so that was the result of our indirect proof, lines 7 through 16. Our indirect proof brought us to the conclusion A horseshoe D. But remember, this is all happening inside a conditional proof whose first assumption, I mean, this is the internal conditional proof 2, whose posit was A horseshoe B. So lines 6 through 17, which started with the antecedent, got us to this consequent, if A then D, demonstrate by conditional proof that parentheses A horseshoe B, close parentheses, horseshoe, parentheses A horseshoe D. That's the result of a conditional proof. But all of that was only possible given the first premise of this proof, the first premise of this proof being in form of a hypothesis or an assumption, the antecedent to this conditional. I won't write the whole thing again at the bottom where you can't see it anyway. Trust me, let's just move that whole conditional up here to the bottom. That is the final line. That is the theorem that we proved, okay, as a conditional statement by the big conditional proof of lines 1 through 18. Okay, that is a combination of conditional proof method and indirect proof method to arrive at the tautological proof of a theorem, not a theorem you use every day, but still a theorem of logic. You can see that the types of conclusions we're able to derive in logic this way are far more complex than the kinds we were working with, whether with rules of inference, replacement rules, or truth trees. For that matter, you might say they have a complexity beyond anything we would use in formalizing an ordinary set of sentences in daily life. Indeed they do. But when you want to be able to derive formulas of this complexity, sometimes there's no alternative but the conditional proof and indirect proof. It will always be an appendix to the main methods that we use for demonstrating validity in sentential or propositional logic. This is never going to carry the weight. This is never going to be the main thing we do in logic. When you're teaching logic, sometime this is never going to be the main technique that you use. But when you use it, you will find, I mean, it's like, maybe you remember the excitement of taking algebra in 7th grade, 8th grade, whenever you took algebra. Or beyond that, the excitement of taking calculus, when suddenly problems that would have seemed incalculable without these new techniques suddenly became things you could really manage. Well, that's how I feel about the conditional proof and the indirect proof too. Thank you.